If you've ever felt like your computer was thinking, you weren't entirely wrong, but the truth is, it isn't just one mind at work. It is a sophisticated collaboration between two distinct types of intelligence. The CPU, you, and the GPU. But why do we need both? Why can't one just do it all? To understand the modern computing landscape, we must first pay homage to the veteran, the brain of the operation, the central processing unit, or CPU. Imagine for a moment a master architect sitting in a quiet office. This architect is brilliant, capable of solving the most complex logical puzzles and making executive decisions that keep an entire city running. However, this architect works alone. This is your CPU. The CPU is the general-purpose heart of your system. Its primary role is to run the operating system, whether that's Windows, Mac OS, or Linux, and handle the myriad of small, complex tasks that keep your applications functioning. When you move your mouse, the CPU calculates the new coordinates. When you type a word in a document, the CPU tells the software how to display that character. It is optimized for latency, which in the tech world means the speed at which a single task can be completed from start to finish. The CPU thrives on serial processing. It takes one instruction, executes it with incredible precision, and moves on to the next. Because it handles the most critical logic of the machine, it must be fast at making decisions. If the CPU hesitates, the whole system stutters. This is why we call it the brain. It doesn't just crunch numbers, it directs the flow of traffic for every other component in the machine. To truly appreciate the CPU, we have to look inside its microscopic walls. Within this tiny silicon chip lie three critical components that allow it to function as the conductor of the digital orchestra. First, there is the ALU, or the arithmetic logic unit. If the CPU is the brain, the ALU is the part that actually does the math. But it isn't just addition and subtraction. It's the fundamental logic of if this, then that. It is the engine of the decision-making process. Second, we find the control unit. This is the middle manager of the chip. It doesn't do the math itself, but it knows exactly where the data needs to go. It fetches instructions from the memory, decodes them so the ALU can understand them, and then directs the output to the right place. Without the control unit, the CPU would be a genius with no way to communicate. Third, we have cache memory. This is perhaps the most underrated part of the CPU. Imagine our architect has a tiny post-it note on his desk with the phone numbers he calls most often. That is the cache. It is incredibly fast, much faster than the system RAM, and it stores the data the CPU needs right this second. By keeping vital information within arm's reach, the CPU avoids having to walk across town to the RAM to find what it needs, drastically reducing latency. While we often talk about system memory, RAM, in the same breath, it's important to remember that RAM is external to the CPU. Think of RAM as a giant filing cabinet in the hallway. It holds a lot of information, but it takes a fraction of a second longer to access than the cache. The relationship between the CPU, its internal cache, and the external RAM is a delicate dance of data retrieval that happens billions of times per second. For decades, the race in computing was simply to make the CPU faster to increase its clock speed. But eventually, we hit a wall. If you make a single processor run too fast, it generates enough heat to melt itself. Engineers had to get creative. Instead of making one architect work faster, they decided to put multiple architects in the same room. This gave birth to the multi-core CPU. Today your computer likely has 4, 8, or even 16 cores. Each core is an independent processing unit, capable of handling its own set of instructions. This shift changed everything. Suddenly, your computer could truly multitask. While Core 1 is busy handling your web browser, Core 2 can be background updating your software, and Core 3 can be processing the audio of the music you're listening to. This parallel execution of separate tasks allows the system to remain responsive even under heavy loads. However, even with 16 cores, the CPU is still a collection of generalists. It is built to handle variety and complexity, not sheer volume. And that is where our story takes a turn toward the visual. As the 1990s progressed into the 2000s, something changed in the way we used computers. We stopped looking at text-based interfaces and started demanding high-resolution graphics, complex 3D animations, and immersive video games. To display a single frame of a modern video game, the computer has to calculate the color and brightness of millions of individual pixels. Each pixel requires math. For a CPU, even a multi-core one, this is a nightmare. It's like asking our master architect to personally hand-paint every single brick in a skyscraper. He's overqualified for the job. And because he can only do one thing at a time, even with a few cores, it would take him forever. The result was lag. The CPU would get bogged down in the repetitive, massive calculations required for graphics, leaving the rest of the system to freeze. The computing world realized it needed a different kind of worker, not an architect, but an army. This realization led to the birth of the GPU, or Graphics Processing Unit. If the CPU is a handful of brilliant architects, the GPU is a stadium filled with thousands of disciplined laborers. While they might not be able to design a skyscraper from scratch, they are world-class at one specific thing, doing simple math simultaneously. The architecture of a GPU is fundamentally different from a CPU. While a CPU might have 8 powerful cores, a high-end GPU might have thousands of smaller, simpler cores. Each of these cores is equipped with its own ALU. This allows the GPU to engage in parallel, processing on a scale the CPU can't even dream of. When a game needs to render a scene, the GPU doesn't calculate one pixel at a time. It assigns a different core to thousands of pixels simultaneously. In the time it takes the CPU to decide what the next line of code should be, the GPU has already finished painting an entire landscape. This is the difference between throughput and latency. The CPU wants to finish one task now. The GPU wants to finish 10,000 tasks at once. For a long time, the GPU was relegated to the graphics card, a peripheral used only by gamers and video editors. But about a decade ago, scientists and engineers had a light bulb moment. They realized that the math required to render a 3D explosion in a video game, linear algebra and matrix multiplications, was the exact same kind of math needed for complex scientific simulations. This birthed the era of GPGPU, general-purpose computing on graphics processing units. Suddenly, the GPU was being pulled out of the gaming world and thrust into the front lines of human progress. In scientific simulations, GPUs are used to model weather patterns or the behavior of molecules in a new drug. In financial modeling, they calculate thousands of possible market outcomes in the blink of an eye. But perhaps most importantly, the GPU has become the backbone of the artificial intelligence revolution. Machine learning and AI development require processing mountains of data. To train an AI like ChatGPT, you need to perform trillions of simple mathematical operations. A CPU would take years to do this. A cluster of GPUs can do it in weeks. The GPU has evolved from a toy for gamers into the most important tool in the modern technological arsenal. To truly grasp the relationship, we have to look at their core differences side by side. It is a battle of philosophies. Function: the CPU is a general-purpose tool. It handles the if-then logic of your life. The GPU is a specialized tool, built for high-volume, repetitive tasks. Processing style: the CPU is serial. It works through a checklist. The GPU is parallel. It works through a crowd. Core design: the CPU has a few powerful cores designed to handle complex instruction sets. The GPU has thousands of simpler cores designed for mathematical throughput. The goal: the CPU prioritizes low latency, speed of completion. The GPU prioritizes high throughput, volume of work. Think of a toll booth on a highway. A CPU is like a single highly efficient lane where the attendant can handle cash, credit, passports, and even give you directions to the nearest diner. It's fast for you, but if 1,000 cars show up at once, there's a backup. A GPU is like having 50 lanes that only accept exact change tokens. It can't give you directions and it can't handle a passport, but it can move 1,000 cars through the gate in seconds. A common misconception is that as GPUs get more powerful, we won't need CPUs anymore. This couldn't be further from the truth. In fact, the more powerful your GPU is, the more you need a strong CPU to manage it. The GPU is essentially a high-performance subordinate. It cannot start itself. It cannot talk to the internet on its own. It cannot manage your file system. The CPU acts as the manager. It prepares the data, sends it over to the GPU with a set of instructions, and says, "Do the math on this and give it back to me when you're done." Once the GPU finishes its massive parallel task, it hands the results back to the CPU. The CPU then takes those results and decides what to do next, whether to display it on the screen, save it to a hard drive, or send it over a network. They do not compete. They augment one another. A computer with only a CPU is slow at graphics. A computer with only a GPU wouldn't even be able to boot up. Understanding the difference between these two components isn't just for tech enthusiasts. It's practical knowledge for the modern world. When you are looking to buy a new computer or upgrade your current one, don't just look at the speed in GHz. Ask yourself what you are actually doing. If you are a writer, a student, or someone who primarily uses Office software and browses the web, your focus should be on a high-quality CPU with good single-core performance. This will make your system feel snappy and responsive. However, if you are a creator, someone who edits 4K video, designs 3D models, or plays modern games, you must invest in a powerful GPU. In these workloads, the CPU takes a backseat to the raw mathematical power of the graphics card. Furthermore, in the professional world, if you are looking into careers in data science, AI, or engineering, realize that the GPU is your primary tool. Learning how to harness parallel processing is the superpower of the 21st century. We stand at a fascinating crossroads in human history. We have created machines that mimic the dual nature of our own problem-solving. The ability to think deeply and logically about one thing at a time, CPU, and the ability to process a massive amount of sensory information all at once, GPU. As we move forward into the world of AI and virtual realities, this partnership will only become more intimate. We are no longer just using computers. We are using distributed neural-like networks that live in our pockets. Now I want to hear from you. Before reading this, did you realize that your computer had such a complex internal team working together? Have you ever noticed your computer struggling with one task while excelling at another? Which do you think is more important for the future of humanity? The logical precision of the CPU or the massive throughput of the GPU? Let's start a conversation in the comments below. I wish you all great health, a sharp mind, and a system that never lags. If you found this journey through the silicon landscape helpful, please subscribe to the channel and hit that notification bell. We have plenty more deep dives into the technology that shapes our lives coming your way soon. Stay curious, stay informed, and I'll see you in the next one.